So, let's talk about graphics cards. You've definitely heard of them, especially if you're into computers or gaming. But what do they actually do? Think of a graphics card, or GPU, as a special purpose computer inside your main computer. Its main job is to take all the data that makes up an image and turn it into something you can actually see on your monitor. It's like a super talented artist, but instead of using paint and a canvas, it uses code and pixels. Without it, your screen would just be a blank, dark rectangle, which isn't very useful. It's the component that handles everything visual. Every single thing you see on your display, your mouse cursor, your desktop wallpaper, that video you're watching, it's all being drawn by the graphics card. It takes binary data, just ones and zeros, from your computer's brain, the CPU, and translates it into the pictures we see. This process happens incredibly fast, dozens or even hundreds of times every second. This constant redrawing is what creates smooth motion in videos and games. So, when you move your mouse, the GPU is working hard to erase the old cursor and draw it in its new spot, making it look like it's gliding across the screen. Now, most computers have some form of graphics capability built right into the main processor. This is called integrated graphics. It's good enough for everyday tasks like browsing the web, sending emails, or watching YouTube videos. It gets the job done for the basics, and for a lot of people, that's all they need. But when you want to do something more visually demanding, like playing a high-end video game or editing a 4K video, that's when a dedicated separate graphics card becomes essential. It's the difference between having a general-purpose tool and a specialized high-performance one. The reason dedicated graphics cards are so important for heavy tasks is that they are designed for one thing: parallel processing. This just means they can do thousands of small, repetitive tasks all at the same time. Think of it like this. The CPU is like a master chef who can cook a complex meal one step at a time. The GPU, on the other hand, is like an army of cooks who can all chop vegetables at once. This ability to handle many tasks simultaneously is perfect for rendering the millions of pixels that make up a detailed moving image in a modern game or a complex 3D model. Let's rewind the clock a bit. Back in the early days of personal computing in the 1980s, graphics were, well, they were basic. The first graphics adapters, as they were called, were pretty simple. Their main job was to display text and very simple shapes on a screen. We're talking about monochrome displays, just one color, usually green or amber, on a black background. These early cards, like the Monochrome Display Adapter, or MDA, couldn't even display real graphics, just predefined characters. It was a world of command prompts and blocky text, a far cry from the rich visuals we have today. Then came a big step forward: color. Cards like the Color Graphics Adapter, or CGA, introduced a splash of color to the PC world, but it was very limited. We're talking about a palette of just 16 colors, and you could only use a few of them on screen at once. The resolution was also incredibly low, resulting in images that were very blocky and pixelated. Games from this era had a distinct look because of these limitations. Still, it was a huge deal at the time. For the first time, home computers could display more than just text, opening the door for simple games and educational software with pictures. Throughout the late 80s and early 90s, things got progressively better. We saw new standards like EGA and VGA, which stands for Video Graphics Array. VGA was a game changer. It increased the number of colors to 256 and bumped up the resolution significantly. This was the era of 2D graphics where everything was flat, like a cartoon. Game developers and artists got really creative within these constraints, making beautiful side-scrolling games and point-and-click adventures. The graphics card was still mostly just a translator, taking instructions from the CPU and painting pixels to the screen one by one. During this 2D era, the focus was on making things faster and more colorful. Companies started adding dedicated memory to their graphics cards, which helped speed things up because the card didn't have to borrow memory from the rest of the computer. They also introduced hardware acceleration for specific 2D tasks, like moving blocks of pixels around the screen or drawing lines. This freed up the main CPU to focus on other things like game logic and AI. It was a crucial step that laid the groundwork for the massive shift that was just around the corner, the jump to 3D. The mid-1990s is when everything changed. This was the beginning of the 3D revolution. Instead of drawing flat 2D images, computers started creating virtual worlds with depth and perspective. This was a monumental task that required a completely new way of thinking about graphics. The CPU alone just couldn't handle the complex calculations needed to draw 3D shapes, apply textures to them, and figure out lighting and shadows. This created a demand for a new kind of hardware, a card that could accelerate these 3D functions. This was the birth of the modern 3D graphics card as we know it. This period saw the rise of companies like 3DFX, NVIDIA, and ATI, who all competed to build the best 3D accelerator. One of the most iconic early products was the 3DFX Voodoo card. It was so powerful that it was often sold as an add-on card that worked alongside your existing 2D graphics card. You'd literally connect your monitor to the Voodoo card and the Voodoo card to your main graphics card. When you launched a 3D game, the Voodoo card would take over and render incredible smooth 3D graphics that were simply impossible before. It completely changed the gaming landscape. With dedicated hardware for 3D, developers could create games with immersive, believable worlds. Suddenly, we had games like Quake and Tomb Raider, which let players explore fully 3D environments. The graphics card was no longer just painting pixels. It was building entire worlds from polygons. It handled tasks like texture mapping, which is like wrapping a 2D picture around a 3D object, and filtering, which made those textures look less blocky up close. These new capabilities led to a massive leap in visual quality and realism, and the race for better graphics was officially on. From that point on, the pace of innovation just exploded. NVIDIA released the GeForce 256 in 1999, marketing it as the world's first GPU or graphics processing unit. This was a big deal because it integrated even more processing steps onto the card itself, like transforming and lighting calculations, further reducing the workload on the CPU. Every new generation of cards got faster, supported higher resolutions, and added new features. We saw the introduction of programmable shaders, which gave developers incredible control over how light, shadows, and surfaces looked in their games, pushing visuals to new heights. Fast forward to today, 2025, and graphics cards are absolute powerhouses. The performance difference between now and even a decade ago is staggering. Modern GPUs from companies like NVIDIA and AMD are packed with billions of transistors and have their own super-fast memory. They can render incredibly complex scenes in real time at 4K resolution and beyond, with frame rates that make gameplay feel buttery smooth. They do this while simulating realistic lighting and reflections using a technology called ray tracing, which was once something only Hollywood movie studios could do with massive render farms. This immense power has had a huge impact on gaming. Games today are not just games, they are stunning visual experiences. We have vast open worlds with realistic weather systems, characters that look almost photorealistic, and physics that make everything feel tangible. This level of immersion is a direct result of the relentless progress in GPU technology. Features like ray tracing create lifelike shadows and reflections that make virtual worlds feel more grounded and believable. High frame rates give competitive players an edge, while technologies like DLSS and FSR use AI to boost performance without sacrificing image quality. But it's not just about gaming anymore. The parallel processing power of GPUs has made them essential tools in many other fields. Professional artists and designers use them to create complex 3D models, animations, and visual effects for movies. Video editors rely on them to accelerate the process of editing and rendering high-resolution video footage. A task that might have taken hours for a CPU to complete can now be done in minutes with a powerful GPU. This has democratized content creation, allowing smaller studios and individual creators to produce professional quality work from their desktops. Looking ahead, the role of the graphics card will only continue to grow. They are at the heart of the artificial intelligence and machine learning boom. The same architecture that's great for rendering pixels is also perfect for training the complex neural networks that power AI. From scientific research and medical imaging to developing self-driving cars, GPUs are providing the computational muscle. So the next time you marvel at the beautiful graphics in a new game or see a cool AI-generated image, you can thank the incredible evolution of that specialized artist inside your machine, the graphics card.